Hello students, did you know sound can actually draw pictures? Well, kind of. Imagine a long glass tube, not just any tube, but one filled with dry lycopodium powder. That's exactly what Kundt's tube looks like. Now, inside this tube, there's a metallic rod clamped tightly at one end and touching a cork piston at the other. When we rub this rod, it vibrates back and forth along its length. This vibration creates sound waves that travel through the rod and jump right into the air inside the tube. To measure the speed of sound in air, we first need the vibration frequency of the rod, which depends on its material, length, and how it is clamped. For a given rod, frequency is constant and is given by F equals V divided by lambda r, where VR is the speed in the rod and lambda r is its fundamental wavelength. Resonance makes sure the same frequency is induced in the air column, so V air equals F times lambda air. By knowing VR from the rod's material and measuring lambda air in the tube, we can compute the speed of sound in air. Lycopodium powder collects at the nodes, forming dusty ridges. The distance between two successive nodes is given by d equals lambda divided by 2. To reduce error, we measure across several nodes, take the average spacing, and then compute wavelength as lambda equals 2 times d average. With the known frequency, the speed of sound is found using V equals F times lambda, or equivalently to dF. Environmental conditions like temperature and pressure can affect accuracy, so correction factors may be applied if high precision is required. Here's a solved example for measuring the speed of sound. The distance between 4 successive nodes is 24 centimeters. That means d equals 8 centimeters. The frequency of the rod is 4250 Hz. Using the formula wavelength equals 2 times d, we get lambda equals 2 times 8, which is 16 centimeters or 0.16 meters. Now, substituting into the velocity equation, V equals F times lambda, we get V equals 4250 multiplied by 0.16, which is about 680 meters per second. This value is higher than the standard, but that's due to measurement or precision error, which is acceptable in qualitative demonstrations. To wrap up today's sound adventure, let's refresh the key points. The speed of sound, V, equals frequency F times wavelength lambda. That's a golden rule for waves. In Kundt's tube, wavelength lambda equals 2 times d, where d is the distance between adjacent nodes. That's how powder patterns reveal the invisible wavelengths. The rod's vibration frequency, F, depends on its speed and wavelength inside the rod. F equals V sub r divided by lambda sub r. Standing waves in air create fixed lycopodium bands, those dusty nodes that cleverly help us measure lambda. Thanks to resonance, the vibrational frequency matches perfectly between the rod and the air column, letting us find sound speed in air. And just like life, experiment accuracy improves when we average measurements and consider environmental factors like temperature, because sound speed changes with how warm or cold the air is. So remember, today we saw how sound waves invisibly etch patterns in powder, how resonance lets us tune between solids and gases, and how math turns these observations into numbers telling us how fast sound really travels. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.